This section is about adaptive system modification. So it is an application of the extended Kalman filter. So let's assume we have a linear system. So with the state space equations, so as usual, so the Kathy and it, they are the process noise and measurement noise. The standard assumption, so they are assumed they are uncorrelated Gaussian white noise sequence. Here we assume this A and gamma and C matrices, so they are known matrices, but with unknown constant vector. Okay, the underlying fit is unknown. So the objective is to identify fit. So here we know fit is a constant. Okay, so we can. So the idea is to consider fit as additional state. So since fit is a constant, so we can have an additional state equation like theta k plus 1 is equal to theta k. Okay? But this book, it mentioned that if you use theta k plus 1 is equal to theta, okay, it will not work. But I have a different opinion about this. I think it will still work. Okay, so the key is not about the equations. Okay, so in my opinion, it will still work. Okay, even though this true state is unknown. Okay, maybe I will explain it later. Okay, I think it will work. Okay, if you use this equation, it will still work. Okay, you don't need to add a random noise. Okay, then let's see. Okay, if we do not add this random noise, okay, will it work? Okay, then if you consider the fit as additional state, then you have this augmented state equation. So this is the original equation. Then you have this new equation. Okay, we do not need to consider this random noise. Okay, so measurement is the same. Okay, then we know to apply the extended Kalman filter. Okay, we need to estimate the initial state. Okay, so for x, we can give an initial state, the initial estimate. Okay, x had 0. Then how to give an initial estimate of fit k. Okay, that is height fit 0. Even though in the book it gives some approach, okay, but I don't think that it's really necessary or really accurate. Okay, it's just a way to approximate. Okay, maybe it will even work if you give an arbitrary estimate. Okay, so now let's see what the approach suggested in this book. Okay, for the first one, they will think, if you look at this equation, okay, this one, okay, if you move vk minus ck, then sit xk, it will be etk. Okay, if you think of etk, it will be a zero mean. The variance is rk. It's a Gaussian sequence. Okay, then there are many different ways. Okay, you can using the data to calculate. Now let's look at what the suggest in this book. Okay, it suggested that if you use, so this is true, okay? So this is true. The expectation of V0 is C0 fit expectation of XK. Then the next part, I think it's wrong, okay? You cannot get this conclusion, okay? So they want to use a data, okay? If you measure data, okay? Then this one is zero mean, it's totally wrong, okay? Because the V0 is a random variable, okay? The random variable, so this expectation will equal to the right-hand side, okay? But if you take a measurement, okay, V0, then you see this is not a random variable, it's a constant. Then you see it's constant minus this a known matrix with unknown parameters, okay? Then the expectation of the initial state, because usually if you know, okay, the expectation of the initial state, so this is a known. If you think this is Z0, it's totally wrong, okay? To approximate the mean, okay, you need to measure many V0, then you take an average. Then this only true, this V0 is the same with expectation of V0, only way you have infinite many the data. Because here, it only want to give some estimation, okay? So one approach, okay? The book use different approach, okay? You can evenly, could just let this be equal 0, okay? Then you can solve, okay? This is a known, so this is a known, only unknown is seed, okay? But I don't think it's very meaningful to do it, okay? But the book also suggests a different way. Instead of using the mean, you can also use a variance, okay? Again, I think you cannot use a data to replace the variance, okay? You have to treat first, you can calculate V0 minus C0, then X0, okay? You can calculate the variance, okay, of this term, okay? It will be R0, okay? That's what it did. But this equation is, I think it's wrong. It's only approximation. When you calculate this variance, then you replace the variance of V0 by the data. I think this step is wrong. It's approximation, okay? You cannot replace the variance of a random variable by only one sample of the data, okay? But this is approximation, okay? So I think it's fine. Okay? It's approximately you can do it, but like me said, okay? You can use any arbitrary estimate of seed height, okay? So this is the one approach suggested in this book. But when you do this, you also need to consider, let's say, the V0 and the X0, they are correlated in general, okay? Then you have to make another assumption that they are uncorrelated, okay? So you can replace the random variable by a single data, okay? Then the book mentioned that if there's no solutions for fit, then you can go to the next step using one more data using V1, okay? I think here it means no solutions. I think it means no real solution. It will fall in the complex domain. It always has solutions. I think here it means no real value solutions. But you can do one more step, okay? This is the equation. Then you replace x1 using this equation. So here, then if you move this to the other side, to the left-hand side, it's equal, then you calculate the variance, okay? So the right-hand side, the variance is R1, then you calculate the left-hand side, as I mentioned, okay? So this V1 here, it is a random variable, okay? Then the approximation is to replace the random variable by a real value, okay? So in general, it's not true, okay? But the approximation is fine, I think. It can give you some equations. You can calculate fit but I don't think it's very meaningful to estimate theta in this way, but it makes some sense that only use one data point to estimate the variance, okay? So once you have an initial estimate of theta, then you can follow this standard, okay, extended Kalman filter procedure, okay? So this is your initial estimate. For initial estimate of the state, you just use a mean, okay? So this is your initial estimate of theta. I think the key here, okay? So in the book, it's mentioned that, so it said if you consider this unknown is deterministic, okay? I think you can do it, okay? It's okay, but this, what you cannot do, you cannot set sk0 as 0, because the reason is that, because since theta is unknown, okay, even though you estimate, okay, if you take sk as 0, it means your estimate is perfect. But here, since theta is unknown, so your estimate cannot be perfect, okay? You must be think the equation is deterministic equation, okay? This part is true. But your estimate must be a random variable, okay? That means this is a random variable. So that means x s0 is not 0, okay? This is not 0, okay? If you treat this as 0, of course, then it's totally wrong, okay? So that's the key. You can still use the deterministic equation, okay? That's in this step. Okay? You do not need to add this random variable, but for initial estimate, okay, the S0, you cannot take as 0, okay? If you take as 0, then as it's mentioned, okay, you cannot go anywhere, okay? So because when you calculate the GK, okay, it will be something like this, okay? GK and 0, okay? There will be no update for the estimate of theta. Okay, then this is just the very standard procedures, okay? This is the state equation, okay? Then this is the standard step, okay? Calculate P, then the Kalman gain, okay? Then update for P, then calculate the estimate.